So again, this is, if you missed it, this is not in the notes. I posted an announcement saying, with a little handout that says, here's what we're going over. So if you missed it, or you don't know where these are, then you can just get out a scratch piece of paper and write things down there, or you can just follow along. I won't be collecting this or anything. I just want to give us the broad strokes and make sure that we're doing things correctly. All right. We are using a 90% confidence interval to estimate. This is what your confidence interval should start with. It should start with this sentence, and the next thing we're going to do, we do this in hypothesis tests as well, is define our parameters. To estimate P1 minus P2. And we need to define what P1 and P2 are. So you may see me writing some shortened versions for the sake of time. P1 is the proportion. Oh, what are we looking at? We're looking at approval rating. So we will have P1 be the, let's see, the two different dates were August 2009 and September 2010. And so then it does 2010 first and 2009. Okay. Where P1 is the proportion of US adults who approved of Obama's job performance in September 2010 and P2 is, and this is where I'm going to shorten for time so you don't have to watch me write all this out, but you get the idea. P2 is the proportion of people who approved of Obama's job performance in August 2009. That's your step one. So we are stating what we're finding, and we are defining our variables. That's the main part of step one. Remember, for hypothesis tests, you still define your variables for P1 and P2, but you also state your null and alternative. That's what you're stating. In confidence intervals, you're going to start with, we are using a 90% confidence interval to estimate. Again, it does not matter which one you make P1 and which one you make P2, as long as you keep them straight in step 3, and as long as you define and distinguish which one is P1 and which one is P2. And this is where we're doing that in step 1. Step 2. First thing we do in step 2 is we say the name of our test. We are doing a 2 proportion Z interval. Imagine what it's going to be called on the calculator. And now we're going to check our conditions. Random. We have randomly selected US adults in September, and we have randomly selected US adults in August. 2 samples. Sorry. Oh, here, that's what I was going to say. 2 samples of randomly selected U.S. adults were taken. In September 2010, we had 1,024. And then in August 2009, N was 1,010.
Do you want us to define N, like when we're actually doing the problems, like in this step?
So we can say, if you wanted to define it further, you could say N1, N2. Because this is N sub 1 and N sub 2. Usually we say what our samples are, and we quote the part that says that we took random samples. In this case, we did take random samples. This wasn't a randomized experiment where we split people into, where we took a group of people and split them. This was actually this was actually 2 separate random samples that we were using. Normal. N times P hat 1. We need to check N times P and N times 1 minus P for both cases. N times P hat 1. Let's see, N1 times P hat 1, that was 1,024 times 0.5. That's going to be 512. N2 times P2 equals 1,010 times 0.53. That one I actually do need the calculator for. $10 times 0.53, 535.3. Remember, when we put this in the calculator in step 3, that's going to be, we're going to round it to 535 because it doesn't like decimals when you put your x1 and x2 in the calculator. And then we do N2 times 1 minus P1, P hat 1. That's also going to be 512.
Do you mean N1 times 1 minus P?
Yes, N1 times 1 minus P hat 1. And then N2 times 1 minus P hat 2. Put hats on there. P hat 2, and then 1 minus P hat 2. That equals 1010 times 0.47 instead. And so that's going to be 400 and something. 474.7. 0.7. All are at least 10. So we can use an approximately normal distribution, or a normal approximation is what I usually say. A normal approximation. Remember, that doesn't mean the distribution is exactly normal. It means it's close enough to normal that we can use z-scores and like normal CDF and inverse norm to get z-scores and all that good stuff in our formulas in step 3. That's what we're saying. Independent. there were at least 10 times our sample size, 10,024 equals 10,240 US adults in 2010, and 10 times 1010 equals 10,100 in 2009. So we can assume independence there. I will not show this much detail in the next one. We'll just talk about them briefly and then move on to step 3. Hopefully we're pretty comfortable on our random normal independent. Just don't forget to say the name of the test here in our step 2. Step 3. Remember, in step 3, our process is going to be formula, plug in the numbers, answer. That's what our step 3 is going to look like. And then when we get back to means next week, we need to make sure that we say degrees of freedom. But we'll get there. Step 3, our formula. Since we're doing a confidence interval, it's going to be our parameter that we're estimating. So, or a statistic that we're using for an estimate. So that's p hat 1 minus p hat 2. Plus or minus our critical value, so that's our z-score, times standard deviation of the statistic. So whatever our standard error formula is. This is in your formula sheet. Remember, it comes from adding the variances. So p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 all over n2. Okay. Plug in our numbers. Equals. All right, remember, our first sample is the 10,024. We have the 50% approval rating. So that is our p hat 1 and our n1. And then the 10,000, not the 10,000, the 1,010 and the 53 are our p hat 2 and our n2. So p hat 1, that is 0.5 minus 0.53. And then plus or minus our z-score. If you don't know what it is, then you would do inverse norm. And then since it's 90%, we want that 90% in the middle. Just a reminder, because we haven't done this in a little bit. That means this middle needs to be 0.9, which means this left, there's 5% on each tail. So our percentile that we actually want would be the 95th percentile. The 90% in the middle plus 5% on each tail. Plus 5% on the left tail. So we have we'd go inverse norm 0.95. It would give us 1.645. And then here comes our standard error formula. And from here, the calculator is going to take it from there. And give us our confidence interval. So we have formula, we have plug in the numbers, and then we're going to get our answer. So on the calculator, we're going to be going to stat tests. And the biggest thing to remember when we go over to stat tests is that we don't want to put decimals in for our x1 and our n1 and all that. So we're going to go stat tests. We're going to scroll past 2 proportion z tests because we're doing a confidence interval, not a hypothesis test. There's 2 proportion z interval. Let's see, I haven't put in for the last one we did. So this is 512 out of 1,024. And then our n times p here was 535. We're going to round it and not put in the decimal. Otherwise, calculator is going to give us an error. And that's out of 1010. Our confidence level this time is 0.9. And again, the calculator should give you back. Here's p hat 1, it was 0.5. Here's p hat 2, it was basically 0.53. Here was your sample sizes you put in. There's the confidence interval. Negative 0.0661. To 0.00674. And so, step 4 is interpret. And again, this sentence really hasn't changed from when we did it the very first time we wrote this sentence. We are 90% confident that the actual and I'm going to say what the confidence interval we're measuring was, what our actual parameter we're measuring is, that the actual difference in approval for Obama's performance between August 2009 and September 2010 is between and then I'm going to give the numbers of the confidence intervals. So that's how our step 4 sentence looks. We're 90% confident, and then say what you were measuring the confidence interval of, and then say it's between these 2 numbers. Same sentence that we've been doing and we've been using. Oh, 0.0661. That's what it was. Not 0.0061. This was a 6 the whole time. And this was a 6 the whole time. Sorry, this is what happens when you rush through the phrasing. They're just little details that get missed. Okay, before I go on, let me talk about part B real quick. Because we've mentioned it before in chapter 9, but we're going to mention it here again. Based on this interval, is there convincing evidence that Obama's job approval rating has changed? This has to do with the linkage between a confidence interval and a 2-sided hypothesis test. So, the main idea is that 90% confidence interval should tell you about a two-sided test with an alpha level of 0.1. If it were a 95% confidence interval, it would tell you about the alpha level of 0.5. So this tells me what judgment I would make at a 0.1 alpha level. Because remember, what the confidence interval tells you is some plausible values for the difference in these two proportions. And if we're measuring a difference in the two, whether there's a difference in the two proportions, our hypothesis test would be about the difference being 0 versus not being 0. So we would look at these two, I won't write out the whole sentence, but we'd look at this confidence interval and say, wait a minute, 0 is in this interval, which means that 0 is a plausible value for my parameter. Therefore, at a 0.1 alpha level, we would fail to reject the null hypothesis. We'd fail to reject our null hypothesis of that there's no difference in between the two approval ratings. So in other words, there wasn't a statistically significant change in Obama's approval rating between this time period of 2009 and a similar time in 2010. That's what the conclusion would be. So this next one, I'm going to be given a medium amount of detail. Are teenagers going deaf? Well, you can still hear me, so I don't think it's quite that bad. In a study of 3,000 randomly selected teenagers in 1988 through 1994, 15% showed some hearing loss. Similar study in 2005 to 2006, 19.5% showed some hearing loss. Data get convincing evidence that the proportion with hearing loss has increased. Oh, increased, that sounds like one-sided. So I'm going to state this null and alternative in two different ways here. I'm going to state it at step 1. This is basically part A, is asking you to do step 1, and then part B is asking you to do the rest. So I'll just write it as step 1. Step 1, our null hypothesis is that P1 minus P2 equals 0. That would be no difference between the two proportions. Okay? Before I go on to state the alternative, I'm going to define P1 and P2. Again, it doesn't matter which one you make P1 and P2. The important part is that you say that in the problem. You state plainly which one is which. All right. P1 is proportion of hearing loss in the study of 1988 to 1994. P2 is the proportion of teenagers that suffered some hearing loss in 2005 to 2006. Again, you would write all that out. I'm just, for the sake of time of this meeting, I'm shortening it to the important detail. So if that's our P1 and P2, then our alternative for P1 minus P2 Well, if we think that the proportion with hearing loss has increased in this time, that means we think that P2 is bigger. We think the proportion in 2005 to 2006 group is bigger. So if we think that the second number is bigger in a subtraction problem, that means the answer would be negative. P1 minus P2 is less than 0. Another way that some people like to state this null and alternative is the null is the P1 equals P2, and the alternative is the P1 is less than P2. In other words, P2 is bigger. If it helps you to write things out that way, then feel free to do that. Again, these are two separate random samples. Again, those populations of teenagers are bigger than that. Again, n times p and n times 1 minus p are going to be at least 10. So for step 2, to see how that's done, I'm going to say see previous example. The biggest difference, the only difference between this one and the last one is that we need to say that this is a true proportion Z test now, since we're doing a hypothesis test. And then our random, normal, and independent conditions would all be the same. Step 3, I will show. Step 3, we're getting a z-score. Value minus mean over standard deviation. Our value here would be p hat 1 minus p hat 2 minus our null hypothesis value. Our null hypothesis says that this is 0 over your standard deviation. The biggest difference in the standard deviation this time is that it uses that pooled proportion that we talked about last time. So this time we are using p hat sub c times 1 minus p hat sub c over n1 plus p hat sub c times 1 minus p hat sub c over n2. That p hat sub c is, remember, it's treating these separate samples as one big sample. And so that would be, if these really are the same, then we can treat it as one big sample and say, let's see, combined between the two samples, there were 4,800. And then I need, let's see, 3,000 times 0.15. You'd have done this in step 2. 450, 195 times 1,800. That's 351. So 450 plus 351 are the combined totals in both samples that suffered some hearing loss. So that is 700, no, it's 801 out of 4,800, which equals 0.167, rounded up. So up here in the formula, meanwhile, we have 0.15 minus 0.195, and then minus 0, over our standard deviation formula, square root 0.167 times 1 minus 0.167 over N1 was 3,000 plus. And then this time it's going to be N2, which was 1,800. And then we're going to put our z-score here. Back to stat tests. Two proportion z-test. This time we had 450 out of 3,000 for our first sample. And we had 351 out of 1,800 in our second sample. And our alternative is that P1 is less than P2. Calculate. There's our P hat sub C, our pooled proportion, treating it as one sample, the 0.167. It gives back our 0.15 and 0.195 that we already know. Negative 4.05 is our z-score. If you want to put it in terms of the probability, since it's a one-sided test, we're using, and our alternative is it's less than, we're using the left tail, so it'll be the probability that z is less than this negative value, negative 4.05. And this is a pretty small p-value. This is times 10 to the negative fifth. So this would be 0.0000258. So that's times 10 to the negative fifth. Again, for step 4, you should be used to this sentence by now, so I'm not going to write it all out. But our p-value is less than our alpha level. Less than, sometimes with a p-value this small, they'll say like, p-value is smaller than any reasonable alpha level we would use. So we're going to reject the null hypothesis. There is convincing evidence that the hearing loss is increased. And then part C is a question about correlation versus causation. It was popular to say that because of the iPods and increase of blasting music in your headphones, that's what's causing the hearing loss. And maybe, but maybe not. So that's a question about being careful about correlation versus causation. There is a difference, there is an increase, but can we say that there was a that was a causing factor? No, not necessarily. I'm going to point out a couple things here. First off, alternative is that P1 minus P2 is greater than 0. So in other words, we want to test whether the financial incentive helps people quit smoking. So if we're making P1 the financial incentive group and P2 the not financial incentive group, we'd expect P1 to be greater than P2, which makes the subtraction problem positive. So you could also say the alternative is a P1 is greater than P2, and the null would be P1 equals P2. Again, it doesn't matter which one you make P1 and P2. If you are doing the P1 and P2, if you switch them, then the alternative also needs to switch directions. Because now the second number would be bigger, and so the alternative would be less than. Step 2, two proportion Z test. The only thing I want to point out here is the random condition. If you say there were random samples of 474 taken, that's wrong. If you say SRS, that's wrong. The random part of this process is that the volunteers, so it wasn't a random sample, but the volunteers were randomly assigned to two equal groups of 439. That was the random part of the process, is the assignment to the groups, not the sample taken. So make sure you say that in your random condition. All right. And then our z-score is even bigger this time, so our p-value is even smaller. It should have been like a times 10 to the -5 or times 10 to the -6 again. So that was less than our alpha level, rejecting the null hypothesis, convincing evidence that the incentives help those employees at the place quit smoking. So the main thing to check here is your z-score. Again, it gets that pooled proportion by saying, well, if they're the same, we can treat this as one big sample of 878, and out of those 878, there were a total of 88 that quit smoking. So that was where we got our basically 0.1 for. Again, we checked n times p and n times 1 minus p in both samples. And there's our z-score, rejecting the null hypothesis because p-value is less than our alpha level.